Welcome to Automation Desk. In today's world, semiconductor is the main material in the construction of every individual solid-state electronic device or integrated circuit. These materials are segregated in two classes. First is single crystal semiconductor, that is silicon, germanium, and the other one is compound semiconductor like gallium arsenide, cadmium sulfide, gallium nitride, gallium arsenide phosphide, etc. Specifically, those constructed by two or more semiconductor materials of different structures. In this video, we will cover the single crystal semiconductor, that is silicon. In electronic industry, silicon semiconductor is the main choice in chip manufacturing. Silicon, a single crystal semiconductor, is represented by the symbol Si with atomic number 14 and atomic weight of 28.08 AMU. It has a total of 14 protons and electrons each, with an electronic configuration of 2, 8, 4 electrons distributed in 3 orbits. Let's look into the Bohr model of silicon atom. Silicon nucleus is positively charged and the negatively charged electrons revolve around it. Electron configuration shows that the electron distribution is in 3 orbits around the nucleus, which are called shells. The outermost shell is known as valence shell. The maximum number of electrons in a particular shell can be calculated by the formula 2n square, where n is equal to the number of shell. Therefore, in the first shell or k orbit, 2 electrons revolve around the nuclei. In the second shell or L orbit, maximum possible electrons are 8. And in the third shell or M orbit, the maximum possible electrons are 18. Hence, the remaining 4 electrons of silicon occupy its third shell. Silicon has 4 valence electrons orbiting in the outermost shell, which is why it is also known as a tetravalent atom. Let's talk about the atomic structure of silicon and how atoms are bound together to form a crystalline structure. In pure silicon crystals, the 4 valence electrons of one atom form a bonding arrangement with 4 adjoining atoms. The sharing of electrons, which strengthens the bond between atoms, is called covalent bonding. Let's discuss how the valence electrons define the conductivity of any materials. Although the covalent bonds create a strong connection between valence electrons and their parent atom, valence electrons can still gain enough energy from external natural sources like light in the form of photons or thermal energy in the form of heat from surrounding to break the bond and enter a free state. These electrons in a free state, known as free electrons or charge carriers, define the relative mobility of material. As the temperature increases, these free charge electrons are available for conduction. This shows the semiconductor's property of having negative temperature coefficient. Around 15 billion free electrons exist in a space smaller than a sugar cube of intrinsic silicon. Let's explore how this semiconductor material conducts electricity. Each atom has specific energy levels for its electron shells. The valence electrons are significantly least bounded to atomic structures as compared to any other electron. The energy band gap, that is, the energy difference between the valence band and the conduction band, varies significantly between insulators, semiconductors, and conductors. Insulators have a large band gap, typically greater than 5 electron volts. This wide gap prevents electrons in the valence band from easily moving to the conduction band, resulting in very low electrical conductivity. Semiconductors have a moderate band gap, usually between 0.5 electron volt and 3 electron volt. For silicon, this band gap is equal to 1.1 electron volts. With some external energy, such as heat or light, this smaller gap allows electrons to cross into the conduction band, making semiconductors more conductive than insulators. The size of the gap indicates how sensitive each type of semiconductor with temperature change. Conductors have no significant energy band gap, meaning the valence and conduction band overlaps. This overlap allows electrons to move freely between bands and gives conductors high electrical conductivity even at lower temperatures. In semiconductors, the energy gap also reveals which elements are useful in the conduction of light emitting devices like LEDs, which will be covered in our next video. If you like this video, simply subscribe to it to see coming new videos.